Hello, this is Dean Horak, and this is a technical overview of the HearSee visual prosthetic system I've recently developed. The device consists of a pair of sunglass frames on which a pair of CCD cameras are mounted. It also contains a set of 4 speakers, 2 on each ear, and a small portable computer to perform the visual to audio conversion. And essentially what happens is within each frame of the video, each pixel is taken and converted from RGB signal to HSV signal, which more closely maps to the color spectrum of the rainbow. This HSV frequency is then down sampled into a audio frequency suitable for human hearing, basically between 200 Hertz and 18 kilohertz. This is done for each pixel, and all these frequencies that are generated are then sent through a software mixer, and this software mixer then projects the output audio signals into the 4 speakers located above the ears of the wearer. For each camera, the bottom portion of the video frame is directed to the bottom speaker of each ear, and the top portion of the video frame is directed to the top portion of the speaker on each ear. And each video channel, the right and the left, are independent of each other. The amplitude or volume of each of the frequencies increases toward the center of the frame and decreases toward the edge of the frame, as we'll see in the next slide. The amplitude distribution basically follows a 3D Gaussian distribution, where the loudest or greatest amplitude frequencies are at the apex, and they diminish as the pixels are located toward the edges. Now, having 2 cameras is important here because it provides enough information for the brain to be able to perform the computation required for image disparity, which is necessary for the brain to be able to form depth perception. The software itself is shown here. This is the current panel showing where we can select the 2 video sources, the right and left camera. We can select the sound card for the top and bottom, each containing a right and left speaker. We can see the 2 video streams as they're coming in real time. We also have the ability to adjust the vertical and horizontal portion of the frame so that we can align both right and left video frames, and we also have the ability to adjust the volume of each of the 4 speakers individually to match those up and account for any variations in speaker quality or sound card variations. Over to the right here, we have the ability to choose the range of frequencies. This will allow us to account for variations in individual hearing capacity. We can choose the lowest and highest frequencies that the system will produce. Obviously, with the greatest range, we get the greatest resolution, and as we squeeze the bottom and top frequency ranges, we lose some resolution, so we want to try to keep that as wide as possible. We also have the ability to choose the use of sine waves rather than square waves for the sound. Sine waves will give a smoother more pleasing sound, but at the cost of higher computation power, which means slightly slower and less real-time throughput. But I found pretty good results just going with the square wave as it is. But hopefully with more processing power, we'll be able to use sine waves just for the pleasure of the wearer. This system has some advantages over existing technologies. Number one being real-time feedback. Some systems do not provide real-time feedback, and in my opinion this is a requirement, because in order for the brain to associate motion with the changes in sound, it is important for the brain to be able to form the associations needed to map the sounds to vision. The system is non-invasive. There's no surgery required. Just the system is comfortable, essentially no more uncomfortable than a pair of sunglasses. The system is inexpensive. Should be able to develop it and get a product on the market profitable to the manufacturer for just a few $100s. There's a lot of room for improvement with this technology. This is the first cut at it. I can see where the visual acuity can greatly be improved by higher resolution cameras, faster frame rates, more powerful processor, can do more sophisticated sound processing. There's even potential for converting some of this to analog, which would be a great improvement in performance as well, and require vastly less processing power to do so. The audio representation can be vastly improved by more sophisticated algorithms, more sophisticated sound envelope type processing. The packaging obviously can be vastly improved by smaller cameras, more aesthetically pleasing frame designs. The wires can be eliminated by using wireless or possibly onboard processor to eliminate anything other than just the glasses themselves. And also battery life will be an issue if the wearer is going to wear this for extended periods of time. That's about all I have on this right now. If you have any more questions, I can be contacted at the email address below, and I hope you found this presentation helpful. Thank you.